Okay, here's a video on the sort and search algorithms. We're going to go through each one of them one at a time, and hopefully you'll kind of get an understanding of them. Mainly you're going to be asked how to basically show the stages of, or kind of describe them, which kind of in a way means the same thing. So let's just have a quick look. Okay, so Vivian has a list of fruit and vegetables stored in a data structure. Grape, pear, tomato, fig, mango, kale, apple, cherry. Identify the most appropriate data structure to store the data above. It is only a one marker, and so therefore you can literally just say array. But let's just have a quick look at it. So they're all data of the same kind of thing. So same sort of like the same thing, and they are all of the same data type. So if it was more than one mark, you would be talking about it being I am able to hold multiple items or multiple similar items that have the same data type, rather than having against one identifier, rather than having lots and lots of individual variables. That's kind of why we're looking at it. So this is an array. It says use a merge sort algorithm to arrange this data in alphabetical order, showing each stage of the process clearly. Okay, so merge sort is what's known as a divide and conquer algorithm. What it does is it divides everything up and then tries to conquer it, or the conquer is the sorting of it. And actually the divide section is where we split all of the original pieces of data, okay, from one array into lots and lots of separate mini arrays. Now, what you've got to understand, or single arrays, like one item, and in the exam they're not going to mark you on the splitting process, they're going to mark you on the merging. Okay, so as long as you show that you understand that they split up. So what happens here is the algorithm splits the array in half into two arrays. Okay, this process is repeated until all of the items are in a separate array on their own. Okay, so I would probably write that to let the examiner know that that's exactly exactly what the process is. Now what I would also do is I would actually put these little square brackets around it to show that you understand they're all in single little arrays. So I'm now just putting all of them into a little array on their own, and if you see, I'm using those square brackets just to be able to show that a little bit more clearly. You don't have to, but if you don't, just try to make it absolutely clear. Okay, now you'll also notice that I have decided to put them as letters instead of the full words. Again, you can put the full words. If you do the letters, you really must make sure there isn't any repeating letters. So for instance, I would just be really sort of like careful if there was two things that had a P, so like pear, but if there was also pineapple, then you'd need to put PE and PI, and if you were putting them into alphabetical order, E becomes before I, so PE, pear, would come before pineapple, so do kind of be aware of that as well. Okay, so we're now at the stage where we have, and I'm just going to split these up a little bit so that it's just easier to kind of see them, but we're now at a stage where we've got all of our items in an array and they're on their own, and it is this stage that you would get marked. One of the marks would be for showing this. So the next thing that you want to do is you want to show that each of the two items at a time would then be merged, and that's the merge sort. This is what they're really going to be testing you on. Okay, so I'm just going to get the arrow, because what you're going to do is you're going to be merging two at a time, like so. And I would put the arrows, okay? So it's kind of like what you're trying to do is you're trying to really show to them that you know exactly the process that's happening. And you need to make sure that you merge them into order. You don't need to know how that actually happens. What you know is that when they merge into alphabetical order. So G becomes before P, so I'm going to do that. So I'm separating them with a comma. I'm just going to copy these two arrows, and I'm going to put those here, and I'm going to merge the T and the F. Okay, so just down here, I'm going to go along here, and you'll know that F becomes before T, so F and then T. Again, I'm just going to copy these arrows just to make sure, it's just so that I can be as quick as possible. And now I'm going to merge M and K, H-I-J-K-L-M, so K comes before M, okay, and then finally let's just get these ones merged, and obviously A becomes before C, so we're going to say A, comma C. So what we've now done is we've done the first merge, in that we've merged each of the two items of data to become a new array, but all of these arrays you'll see are now in order. We've merged them in order. What we then are going to do is we're going to then merge two of these arrays together. So again, I'm just going to grab my arrows again, and so we're now merging these two arrays together, and we are going to merge them into order. So F comes before G, so F, G, and then P comes before T, P, T. And so you're merging these two into alphabetical order. Once again, we merge these two, and let's just move across here, and we're merging these two into alphabetical order. We know that A and C, and then K and M. And then finally, our final process here is merging these two final arrays to become one more array. So I'm just going to grab another arrow, and then I'm just going to make these ones look a little bit bigger. So these are going to merge into this new final array just here. So let's put that here, and it merges into order. So A, C, and then you'll see here F, then G, then K, then M, then P, then T. Okay, so you have to make sure that you know your alphabet, and then just merge them into order. So A, B, C, D, E, F, G, H, I, J, K, L, M, P, T. And it's this process that the examiner will be looking for. Now this question here was given 3 marks. I would suggest you'd possibly get 4, but what they are going to be looking for is this line here, that you know that you're going into separate arrays. This line here where you're showing that 2 items get merged, 2 items get merged, 2 items get merged, and so on. And then this line here where we're showing these 2 lines getting merged again. I doubt that they will mark you for a final sorted array, because some people might just go, oh, I'm just going to write the array back into order, and so they might not just give that mark. But that basically is your merge sort. If you want to show that initial splitting, it's the same principle. It's you split them in half and half and half and half until you get to the single items in an array. Okay, but this is the merge part where you get the marks. Right, now I know that we actually need to use this for the next question, so I'm just going to copy this across. Okay, so I'm now on the next question. I've brought now the fully sorted list back into this one. You would be on the same page here and you'd be able to see this. And I've actually changed what I'm searching for, because they asked us to search for something, but I would like to show you how to search for this one. So it says, show the stages of a binary search used on the sorted list to find Fig. And remember, it will always put it in speech marks, because these are all string data types. If you were actually writing them in array, you would actually put them as string. Each one would be put in speech marks. So a binary search is also known as a divide and conquer algorithm. So the binary search and the merge sort are both divide and conquer. What that basically means is each time you go through the array, so each iteration, you halve the number. And so basically you're dividing the number of items that you're looking for and then trying to conquer it that way. So divide and conquer, if you can try and remember that. So merge sort divides it and then conquers it. Binary search, we're going to see, will divide it and then look to see what's happening, divide it again, divide it again. So what we're going to be doing is we're looking for fig. Okay, so the first thing you do is you find the middle item. So we've got 1, 2, 3, 4, 5, 6, 7, 8. We've got an even number of items, and so actually the middle item doesn't exist. Okay, so the middle is just here. So what you need to do is you need to just fall down and you'll see that it's grape. Okay, so we're actually showing the stages of this, and so I'm just showing what the algorithm goes through. So find the middle item, and I'm going to then say which is grape. Okay, what we're then going to do is we're going to look to see, is grape what we're looking for? So is the middle item what we're looking for? Now they will ask you to use it on a list. They will give you a list, an array of items, and they will say use the list to show it. So write the words or the numbers that you're actually using. So like I'm doing, is grape equal to fig? I'm going to say no, it's not. So then I'm going to say is grape greater than fig? Oh. Okay, is grape greater than fig? Well, yes it is. Okay, G comes after F. Okay, and so we are going to say yes. Now the important thing here, you must know that binary search has to be in order. The data has to be in order for binary search to work, which is why we had to run the merge sort on the data before we could do the binary search. So we're doing the search. It's on an ordered list, which basically now means that we can, because grape is larger than fig, we can discard grape because we know grape is not what we're looking for, and we can discard all items greater than grape, because all items greater than grape are going to be greater than fig because it's in alphabetical order. So if grape is greater than what we're looking for, then everything greater than grape is also greater than what we're looking for. So we discard everything and we create a new list. So a new list created. Okay, and this is that idea of the divide. Okay, we are dividing and then conquering. So we've now got apple, cherry and fig as our new list. Okay, so this is now our new list. So you'll see we have divided that list straight away. We've only done one kind of search so far, one iteration of the binary search, and we're already halved the number of items we're looking for. So we've got apple, cherry and fig, and we start again. So repeat. So find the middle item, which now is cherry. Okay? Is cherry equal to fig? So I'm just doing exactly what I did up there. No, cherry is not equal to fig. Is cherry greater than fig? Well, cherry is not greater than fig. Cherry is less than fig. So we're going to say, no, it's not greater than fig. It's less than fig. So we know that we can discard cherry because it is not equal to the thing we're looking for. And all items less than cherry, which is basically meaning we'll get rid of apple as well. So we now have a new list. We've discarded cherry and apple, and so we now have a new list created, which is now fig. And we're going to start again. So we find the middle item. So find middle item. I know it sounds a bit strange when there is only one item, but the middle item is now fig. And so now you can say, is fig equal to fig? And we can say, yes, item found. Oop. stop search. Okay. Now, if the item was not in the array, which might be the case, they might ask you, well, how do you know when the item, how can you be sure the item is not in the array? And basically it is when you've got down to this one final item, and so therefore that one single item is the middle item, and it's the one you are checking to see if it is equal to what you're looking for. So if that one single item is not equal to what you're looking for, then you know for a fact that the item was not in the array in the first place. So that's that. We've now stopped search and we are going to move on to the next question. So we've now found fig in our array using the binary search, that divide and conquer, breaking in half and conquering over and over and over again. Okay. Give one other searching algorithm that Vivian could use. There's only two search algorithms that you need to know, and that is linear and binary. We've just done binary, therefore linear search is the other one. Now, linear search does not need the list to be in order, so we could have actually used linear search on the unordered list before we put it through merge sort, but linear search is not as efficient as the binary search, especially on long lists. If you think about it, the divide and conquer is what really makes the search of binary search much quicker. If you had 1 million items, you only have to go through one iteration of binary search, one time through it, and you've already reduced the list to 500,000. You've already reduced it by half. Whereas in the linear search, looks at the first item, then the next item, then the next item, then the next item, and if basically you don't find the item, or if it's at the very, very end, you will have done 1 million searches. So binary search is much more efficient. Right, let's move on. Okay, so now we're being asked to do that linear search. So let's have a look at this. Every 5 minutes, an app on a mobile phone records the electrical current in MA, passing through a pair of connected headphones. A sample of the reading is shown in the table below. Now, I quite like this because it is important to understand that just because it's got numbers and letters, you can still do a search or a sort on this. Basically, if you've got a mixture of numbers and letters, it becomes a string. And so you will see here that they've put 12 MA in speech marks. Okay, so it's a string, and basically you just look to see at the first character, and if, for instance, there were two 10s but the letters were different, you would just look at the first letter, and if it's an A, it's lower than a C, for instance. If I'm honest, these ones would just be kind of just looking at the numbers. Okay, so a linear search, as I said, remember the word linear, it gives it away a little bit because you go in a line. You do the first item, you look to see if that is it, and then the next, and then the next. So I think probably in this case, you want to be quite clear to the examiner you know what's happening. So you might want to say compare first item to search item, and then you say is 10 MA equal to 12 MA, which is what we're looking for. And you can say no. So then compare the next item to the search item. So what we're doing is we're letting the examiner know that we're just going through the array one after the other. So then you go is 15 MA, which is the next item in the array, equal to 12 MA, our search item. No. So compare the next item to the search item. And again, we're going to give that example. So is 12 MA equal to 12 MA? And yes, it is. So then we can say item found, stop search. Okay. Now again, so we found the item here, but let's say it was looking for, let's say, 21 MA, and it's not in there. So you would know that if you got to the last item and that is not the item you're looking for, then the item is not in the array. You'll see here that this is not a sorted list, so I would not have been able to do the binary search on that. That's why we were asking to do the linear search, and it's really important to really be aware of that and make sure you look to see whether it is in order or not, so that you have to do the right search on it. Okay, moving on. So we've got another sort algorithm. Jordan is writing code for a travel website and needs to choose suitable searching and sorting algorithms to use. He uses the following as test data. So Jakarta, London, Cairo, Minsk, Amsterdam and Bangkok. Show the stages of an insertion sort to put this list into alphabetical order. Okay, so what I'm going to do is I'm going to make it a bit easier, and I'm just going to use the letters again. But be aware again that if anything, for instance, had the same first letter, again you would then just move and look at the second letter. So we've got J, L, C, there isn't any with the same letter here though, A and B. Okay, just actually going to center this a little bit. Okay. So the most important thing when we talk about the insertion sort is we look at the very first item, or we don't look at it, we just say that the very first item is the sorted part of the list. It's still part of the same list, okay? Still part of the same array, but we just say that the first item is the sorted part of the array. So I'm just going to say here, sorted list. I'm going to make that a bit smaller. And I'm just going to pop that there and put a little arrow showing to the examiner I know exactly what I'm talking about. So J is the sorted list. Now the way insertion sort works is that you only ever look at the first item in the unsorted list, and you insert it into the correct place into the sorted list. Now that just so happens to be after J, in this case, JKL. So we're going to, and I'm going to use the underline to show that they are what I'm looking at the moment. So J and L are now part of the sorted list because I've inserted L into the list. Okay, I have done nothing with the other items, and that's what the examiner is looking for. So again, what we're going to do is we're going to look at the first item in the unsorted list, and we're going to insert it into the correct place, into alphabetical order, into the sorted part of the list. And you'll see that C goes before J in the alphabet. So C, J, L, and I've underlined them to show that they are my sorted list. For M, A, and B, I have not looked at yet. So let's move on. I look at the first item in the unsorted part of the list, and I want to insert it into the correct place of the sorted list, and it so happens that M comes after L. So again, we're staying with the C, J, L, but now we know that M is in the right place, but we have not looked at A or B yet. Then we're going to look at the first item in the unsorted part of the list. We're going to insert it into the sorted part of the list, and obviously A comes before C. So A, then C, then J, then L, then M. And again, we still haven't done anything with B. And then finally, B is the item in the unsorted part of the list, and we're going to insert it into our sorted list. So we've now got A, B gets inserted there, C, J, L, M. And we now have a sorted list. The really important thing here is we are just inserting one item at a time from the unsorted part of the list, and we're inserting it into the correct place. So what you should have then is, if you can make it really clear to the examiner, the underlined part is the sorted list. You then have a really, really nice showing the stages of. And that's worth, this one here is worth 4 marks, so it's a really, really good one to get right. Okay, Stephen has stored the names of the countries he has visited in an array named countries. Now, in your exam, they'll probably say in an array with the identifier countries, because this is an older version. Now, I've also rewritten this array because the original one just would have taken so long to sort, and I don't think that was realistic for the exam, so I've just rewritten it a little bit here. So here we go. Explain why an array is a suitable data structure to store this data, and it's worth 2 marks. So they've told us it's an array, they're asking us why is it a suitable data structure. So we know that an array allows us to holds multiple variables or multiple items of data under one identifier. Under one identifier, all of the items are common, like they have a common, they're common to each other. So these ones are all countries and are the same data type. It's explaining why we want to use it. So the reason why is because this is much more efficient than using many individual variables. Because if I didn't have it in an array, I would have to have country 1 equals, country 2 equals, country 3 equals, and I would just basically put each one of these items against an individual variable name. So that would be a perfect way of being able to explain why we use an array to store this type of data. It's all of the same data type. It's kind of all, they've all got like a commonality. They're all countries, and we're holding, the array holds multiple items of data under the one identifier, and it's much more efficient than using many individual variables. Okay, so let's now have a look at answering the the next question. And it says, show the stages of a bubble sort algorithm when applied to the data shown in figure 3. So again, I'm going to rewrite the array so that it's a bit easier for me to write, because you've got to remember you've got to write the words over and over again. So I'm going to say PLACIN. So this is the initial array, PLACIN. And so we're going to use bubble sort to put these into order. So I'm just going to show that this is the starting point. So I'm just going to put it in bold there. And then I'm going to use underline to show what items I'm working on at a time. Now with bubble sort, we only ever look at 2 items of data at a time. And we work through the array 2, then 2, then 2, then 2. And we swap them if they need to be swapped. So let's have a look. So the first 2 items are P and L, and we put them into alphabetical order. So L becomes before P. So I am going to underline L and P, and I'm swapped them to be in the right order. What we've got to make sure the examiner is looking to see now that you do nothing with the rest of the array. Okay? So A, C, I, and N, nothing has happened to them. What we then do is we move across and we look at the next 2 items of data, which in this case are the P and the A. And we look at them and we see if they need to be swapped. We don't do anything with L, so L stays like that. But it's the P and the A, and they do need swapping, so we'll swap them. And we've underlined it to show that they are the items of data that we were working on. We don't change anything else. Now we're looking at the P and the C. And we're going to swap them if needed, which is needed. So we're not changing L, we're not changing A, but we are swapping the C and the P over. We're not looking at I or N. So again, the idea is we only ever look at 2 items of data at a time, and we swap them if needed. So now we're looking at the P and the I, and again they do need swapping. So L, A, C, we're not looking at, but I and P are what we have looked at and what we've swapped. We've not looked at N. And then finally we're looking at the P and the N, and again they do need swapping. So that P has literally moved all the way along to the end. So we've got L, A, C, I, and then we've got the N and the P. And you'll see that we've kind of got this idea of it bubbling through, which is kind of why it's called bubble sort, I think. Okay, now that's still not in order, and this is what the examiner is also looking for. So they're looking to see that you're only looking at 2 items at a time and swapping them if needed. And then the idea is that we start again and we look at again the first 2 items, so in this case the L and the A, and we will swap them if needed. So they do need to be swapped, so we are going to put them into order, and then we're not changing any of the other data. Now again we're looking at the L and the C, and we know that C becomes before L, so we're going to swap them, but we're not looking at anything else. We're now looking at the L and the I, J, K, L. They do need swapping, so we're going to swap them like so. And N and P we're not looking at. Then we are now looking at the L and the N, J, K, L and N. L and N are in the right place, so we're going to keep them as they are, but we're still underlining them to show that we've looked at them. And then we've finally got A, C, I, L, and then we're looking at N and P, but they also do not need swapping. Now, even though we can see quite easily that this is now in order, we must make sure that we let the examiner know that the algorithm would still go through, it would do the whole thing again, and it would only stop once there were no swaps whatsoever. So something we could write is the algorithm would run through the whole array again until there are no swaps made. Once there have been no swaps, it will stop, as the data will be in order. If you think about it, if we go through and check every single one, and they do not need to be swapped, so it would check A and C, they're in the right order. It would check C and I, they're in the right order. It would check I and L, they're in the right order. L and N, they're in the right order. N and P, they're in the right order. No swaps are needed at all. So once it goes through the whole array again, and no swaps are needed, then we know that the array is in order. And that's where it would stop. And so that is your bubble sort. I hope this has been helpful. This has been all of the, let's just go back to the beginning, all of the sort and the search algorithms that you need to know. Okay, so we've had the merge sort, where we break all of the items into individual mini, like little arrays, individual arrays, and then we merge them together into order. We have got the binary search, where we look for the middle item, and then we look to see if it's greater than, or if it's equal to what we're looking for, and then if it's greater than what we're looking for, and then you can remove either all of those greater than it or all of those less than it. Again, remember, merge sort and binary search are known as divide and conquer algorithms. Then we've got the linear search. The linear search just looks at the first item and sees if it's what we're looking for, then the next item, then the next item, and then the next item, and so on. We have got the insertion sort. The insertion sort says, let's make the first item our sorted list, and then we always just look at one item, the first item in the unsorted list, and we insert it into the sorted list into the right place. Okay, so you'll see there we only ever move one item at a time until we've inserted each one on its own. And then finally we've got the bubble sort, and you'll see that we just look at 2 items at a time and we swap them if needed, but we have to keep iterating through until we have put them into the right order. You can probably already guess a little bit which one's the best. Merge sort, being a divide and conquer algorithm, is actually the most efficient algorithm the most efficient sorting algorithm on very large lists. There's not very much difference actually when the list is really small, like the ones we've got here. But when we're talking thousands, if not millions of items, merge sort is much, much more efficient, being the divide and conquer algorithm. And then with your two searches, binary search and linear search, your binary search is much more efficient than linear search, especially on large lists. And again, the binary search is the divide and conquer algorithm. So if you can remember, the divide and conquer algorithm is always going to be the one that breaks it in half each time and makes the list smaller. So it's just looking at a smaller number of things, makes it much, much quicker to or more efficient to do its job. I hope that's been helpful. I will see you soon.